All right, so today we're going to do two things. We're going to solve 2 by 2 matrix equations, and then we're going to use transition matrices to solve problems. But we're going to start with an equation that we've done similar to a couple of assignments ago, where we just want to find what x is. And so I can solve this equation simply by subtracting this matrix from both sides. So if I subtract this matrix here from the left side, these will undo each other, and I'll just have 1/2 x. But then I'm going to have to subtract that matrix from this side. And so if I take the 1, the -7, 8, and 5 and subtract it from this matrix, then I will have 4 minus 1 is 3. 3 minus -7 is positive 10. 2 minus 8 is -6. And -9 minus 5 is -14. Then I want to undo multiplying by 1/2, so I'm going to multiply by 2. Those are inverses of each other. 2 times 1/2 is 1 times x, and 1 times x is just x. But then I'm going to have to multiply this matrix here by 2. And when I do that, 2 times 3 is 6, 2 times 10 is 20, 2 times -6 is -12, and 2 times -14 is -28. And so my solution, my x matrix, is 620, -12, and -28. How is that different than what we're going to be doing today? Well, it's the same in that we're going to find a matrix x. But instead of getting rid of like 1/2, we have to get rid of this matrix. So that means we're going to have to find the inverse of that matrix. And so the first step in that process is to find the determinant. And that's AD minus BC. A times D is 7 times 2, that's 14, minus B times C, that's the 3 times the 5, which is 15. And that gives us -1. So our determinant is -1. But then the second step in the process is to take 1 over the determinant, which is 1 over -1, and multiply it times a new matrix. And this new matrix is going to be where the 2 and the 7 switch places, the 5 becomes negative, and the 3 becomes negative. So when I take -1 times this matrix, I will get -1 times 2 is -2, -1 times -5 is +5, -1 times -3 is 3, and -1 times 7 is -7, and this is my inverse. So if I were to multiply this inverse times this matrix here, I should get 1, 0, 0, 1, which is the identity matrix. 1, 0, 0, 1 times x is just x. So on the left-hand side, I will just get x. But then I'm going to have to take this inverse matrix and multiply it by the other side, which means I'm going to take -2, 5, 3, that's a 3, and -7. And I'm going to multiply that times -9, -4. Notice I have to put the inverse matrix first. I can multiply, that's a 2 by 2 matrix, that I'm going to multiply it by a 2 by 1 matrix. I couldn't do it the other way around. I have to put that matrix first, and my resulting matrix is going to be a 2 by 1 matrix. And so I'm going to multiply the first row times the column. -2 times -9 is +18. 5 times -4 is -20. And so that's going to give me, in my first spot, a -2. Then I'm going to take the second row times the first column. 3 times -9 is -27. And -7 times -4 is +28. +28. And when I add those together, I get a +1, which means the x that I'm looking for is -2, 1. And we could substitute that back in here for x, multiply it out, and make sure that we indeed get -9 and -4. Let's try this on a little bit bigger of a scale. Same thing as before, except this time we end up with a 2 by 2 matrix instead of a 2 by 1 matrix. And so again, we want to get rid of this matrix, so we're going to have to find the inverse. The first step again is to find the determinant, and the determinant is going to be A times D, that's 3 times 3, which is 9, minus B times C, well that's -4 times -2, which is +8. 9 minus 8 is 1. So that means we're going to take 1 over 1, which is 1, times the new matrix, where the 3's switch places, and the -2 becomes a +2, and the -4 becomes a +4. So 1 times this matrix is itself. And so this is my inverse matrix. So I can multiply that inverse matrix times this matrix, get the identity matrix. The identity matrix times x is just x. But then I also have to take this inverse matrix, which is 3, 2, 4, 3, and multiply it times the existing matrix on the right-hand side, which is -1, -1, 2, and 3. And so if I start with this row times this column, I am going to have 3 times -1, which is -3. 2 times 2 is 4. If I add those together, I get 1. Then I'm going to multiply the first row times the second column. 3 times -3 is -3. 2 times 3 is 6, and I will get a 3. Then I'm going to move to the second row. 4 times -1 is -4. 3 times 2 is 6. That gives me 2. And then 4 times -1 is -4. 3 times 3 is 9, and that gives me 5. So my matrix is 1, 3, 2, 5. And again, we could check it by plugging it in for x, multiplying them out, and we should end up with this matrix here. So that is an example of how we solve 2x2 matrix equations using the determinant. So let's move on to transition matrices. We have one problem here that I want to discuss with you, and we're going to talk about what a transition matrix is and how we can use it to answer these questions. So we're going to assume that cell phone usage trends are that 90% of people who have a cell phone 1 year continue to have it the following year. Also that 40% of the people who do not have a cell phone get one the following year. So a real quick picture of this is this. We have people who have cell phones and people who have no cell phones. And so this would mean that of the people who have a cell phone, 90% of them continue to have a cell phone the next year. But for whatever reason, maybe they break it and they decide not to replace it, 10% of them decide not to have a cell phone the following year. Of the people who do not have a cell phone, if 40% of them move over and get a cell phone, that's 40%. That would mean that 60% continue to not have a cell phone the following year. And so this is what this would look like in a transition matrix. Transition matrix just describes the trend going from one situation to the following year. And so we have, if you do not have a cell phone, 60% of the people who do not have a cell phone continue to not have a cell phone the following year. Which is this number here. 40% of them get a cell phone. So they move to a situation the next year where they have a cell phone. Then if we look at the people who have a cell phone, 10% of them move to where they don't have a cell phone the following year, and 90% of them continue to have a cell phone the following year. So this is what's called a transition matrix. Then it also says here that let's assume that right now we have 70% of the population has a cell phone. So that means if 70% has a cell phone, 30% do not have a cell phone. So we're just going to say this is out of 100. 70 out of every 100 people have a cell phone. 30 out of every 100 people do not have a cell phone. And so we can call this matrix A here. That's the transition matrix. And this matrix B, which is the matrix that we have right now. And so what we want to do is figure out what percent of the population will have a cell phone in 1, 2, and 5 years. And so that's what we're going to work on first. And if you follow through this first one with me, we're going to take this first row here and multiply it times this column. Here's what we're doing. 30% of the people don't have a cell phone. 60% of those 30 people will continue not to have a cell phone the following year. And that's 18 people. Then these 70 people who have a cell phone, they're going to move to the following year. 10% of them will not have a cell phone the following year. 0.10 times 70, that's 7. So if we're looking to find the number of people who do not have a cell phone the following year, we're going to have 18 plus 7, 18 from the people who don't have a cell phone this year that will continue not to have a cell phone, and 7 of these 70 people who have a cell phone this year will get rid of it next year, and 18 plus 7 is 25. Similarly, we can do the same thing if we want to figure out how many people will have a cell phone the following year. We're going to multiply this row times the column here. And so there's 30 people right now who don't have a cell phone. Well, 40% of those people are going to move and get a cell phone next year. 40% of 30 is 12 people. And then 70% of the people who have a cell phone right now, 90% of them will continue to have a cell phone next year. That's 63. And if I take 12 plus 63, that's 75 out of every 100 people will have a cell phone the following year. So essentially what we've done is we've taken matrix A times matrix B, and that gave us the distribution of who has cell phones and who doesn't have a cell phone in 1 year from right now. So let me show you how to do this on a calculator. So on our calculator, the first thing that we want to do is enter these matrices. We have a matrix button on our calculator. So we're going to go to second matrix, and we want to edit this matrix. We're going to edit matrix A, and so I'm going to click enter here. I want it to be a 2 by 2 matrix. It probably is a 1 by 1 if you haven't done this before. So it's a 2 by 2 matrix, and I want that matrix to be 0.6, 0.1, 0.4, and 0.9. So you want to enter all those things into your calculator. And then to get out of this menu, you can just simply go to second and quit. So we have matrix A in our calculator, which is our transition matrix. I'm going to call this matrix here matrix B. So I'm going to go back to the matrix menu. I'm going to move over to edit, and I'm going to go down to matrix B. And I want this one to be a 2 by 1 matrix, and it's going to be 30 people and 70 people. So as soon as you've entered all of those values into your calculator, then you can go to second and quit. And to do what we just did by hand on your calculator, you would just go second, go to your matrix button and choose matrix A, and then times matrix, go down and choose matrix B. And if we do that, we get 25 and 75. So if we think of this as A times B equals C, what I want to do to get the 2-year distribution is take A times C, because we're going to assume that all of these trends continue. But if C is A times B, then that's the same thing as saying A times C, but if we replace C with A times B, then I can say it's A times B. In other words, in 2 years, it's going to be A squared times B. In 3 years, following that same logic, it would be A to the 5th times B. Let's show how this would look like on a calculator. So on a calculator, to get the 2nd year distribution, we would go to the matrix feature, go to matrix. We're going to choose matrix A, but this time I'm going to square it. And so it's matrix A squared times matrix B. And I'm going to scroll down to matrix B and press enter. So now when I press enter, in 2 years, the distribution is going to be 22.5 and 77.5. If I wanted to figure out the population distribution in 5 years, I would go to matrix, choose matrix A, raise that to the 5th power, and then go back, go to the matrix menu again, scroll down to matrix B, and in 5 years, the distribution is going to be about 20.3 and 79.7. The equilibrium would be, eventually this is going to equal out. If these trends never change, now they'll change from year to year. More and more people, cell phones will become more and more popular or less and less popular. But if these trends continue, then I could do something like this to find the point of equilibrium. Maybe I can go to matrix A, and instead of raising it just to the 5th power, maybe I can raise it to the 50th power. And then multiply that times matrix B. And if I did that, we can see that it's not going to get much different than 20 and 80. And that we might reach the equilibrium point not in 50 years, but maybe in 20 years. But that's how we would reach the equilibrium point, and we can predict trends in things like cell phone usage and other things that you'll see in your homework when we start our homework assignment. And that's one example of a transitional matrix. We'll talk more about it tomorrow in class. We'll see you then.